Good morning. Welcome back to ECE 440A, 540A. I don't know if the class is going to be stable or not. I guess for your seating, you're in the left half plane, but for me, you're in the right half plane. So we'll have to see where we go relative to this lecture. Homework 8 is due on the 5th of December. I think that's next Friday. That's a week after Black Friday is when that's due. And remember, D2L has issues late Friday evening. You might just plan ahead that way. Lab number 3 and your project, if you're doing a project, those are due on Sunday evening following that Friday. That's the 7th. And if you need any more additional Bode plot material, I tried to load up in Unit 8 a sort of supplemental block of material that walks you through from the beginning on Bode plots if you would like to have that. There's videos and notes dealing with Bode plots, and I think I actually sort of consolidated it into a submodule, so you won't see much until you click on that submodule, and I'm not sure how you will see it anyway on your student D2L account, but it should be there. And if some of the links are not working or you're missing something, let me know relative to that material. But that's from earlier classes that I've created, and I thought it might be helpful if you just wanted a quick review. As a reminder, teacher course evaluations, I think, became active this week. Those are due on the last day of class, which is the 10th of December. So make sure and do that. Those are helpful for me to figure out what to change, what to continue doing, what to rework, etc., relative to this class. And our final exam is a week after the last day of class. It's on Wednesday the 10th, or I'm sorry, Wednesday the 17th, and it starts at 8 a.m. We won't have to get up any earlier to make it to that exam. You will have to extend longer in terms of sitting here. It will be a 2-hour final exam. Today what I want to do is work through or go through a quiz. Maybe I should have called this a warm-up exercise since it's that time of the year. We need to warm up as we get started. But that's on stability margins. We quickly went over that last time, and I want to make sure that we're comfortable with that terminology and identifying how we can perform or find these stability margins. Then we will talk about system identification. We did system identification in lab number 1, but we did that in the time domain. We kicked the system, we hit the system with a step, we saw how it oscillated, and we said, that looks like a second order system. Let's identify some parameters in that particular second order model. Here, we are going to look at the frequency response data and say, can we infer gains, poles, and zeros from that and obtain a transfer function, G of S, from the Bode plot? Can we sort of back out? So far, maybe in your educational process, you've taken a transfer function, G of S, and generated a Bode plot. Now we want to go the opposite way. You may have a network analyzer or a system that you've now measured data from, and you now have the magnitude and phase as a function of frequency, and you want to find what's my G of S. That's what we will talk about. What's the transfer function? And then we will get into phase lag controller design. And when I say phase lag, you might be thinking, oh, we're trying to address steady state accuracy. We're interested in tracking behavior. That's usually what comes to mind when we say phase lag. And if that's the case, then we are looking at low frequency gain generally. What's the gain at low frequencies? And in a Bode plot, that means you're looking at the left side of the Bode plot magnitude and saying, is this the value I need in terms of magnitude? Those are some issues that will hopefully become a little bit more clear as we go. So here's the quiz. I'll give you a couple of minutes to find the gain margin and the phase margin for that system. Is it large enough? Can you see it somewhat? You have young eyes, and it looks better on the screen or on the projected image than it does on my screen for me. But identify the gain margin and the phase margin for that system. Go. I know it's hard. I should have it so you can just start scratching on something on your page. That would make it easier. But sort of eyeball it and see if you can come up with a gain margin and a phase margin and write some numbers down. And as I began today's lecture, I said relative to my diagram, everyone's in the right half plane, so I don't know how stable this lecture is going to be. But for whatever reason, this morning, all of the students, the X's, are in the right half plane. Maybe if you were zeros, it would be okay, but it would still be non-minimum phase, wouldn't it? If you're in the right half plane. Sorry, I'm maybe making you lose concentration on this gain margin, phase margin quiz. Did you finish? Do you have a number? And if you did, what are some numbers or points on these diagrams that you need to focus on? When I say stability margins with a Bode plot, what are you thinking? Okay, you're looking really at two different points, aren't you? Because all of these stability margins are based on this idea of 1 at minus 180 degrees. The top curve gives you the magnitude, and you're saying, oh, where, and these two plots give you magnitude and phase. You are basically saying, how close are we to 1 at minus 180 when we look at these two plots together? And since we have two plots, we really have two different critical frequencies that we could analyze or look at. One of those frequencies is where the magnitude is 1, and we call that the gain crossover frequency. But on a dB scale, where is the magnitude 1? At 0 dB. One of the first things you want to do is try to find where are we crossing 0 dB with the gain curve, and that's our gain crossover frequency, omega sub g. And what is omega sub g, roughly? I mean, you're doing this from a distance from the screen, but what does it sort of look close to? And remember, these are grids now on this Bode plot, and it's a logarithmic scale, but each line is showing us a new numerical value. We've gone beyond 10 to the 0, which is 1, and we're not yet to 10 to the 1, so we're between 1 and 10 in terms of omega. And it's actually very close to the first vertical line, which is 2. So our gain crossover frequency in this particular system is 2 radians per second. Now to 10 points, that might get you 1 or 2 points, which is better than 0, right, on the final. The other point that you can identify is the phase value, and now you're looking at where does the phase curve cross minus 180, because again, you're trying to find where are we going to have the magnitude and the phase simultaneously satisfying 1 at minus 180. Well, here we go over to 180 and we say, oh, that looks like it's about right there, and we say this is our phase crossover frequency. And what is that? 20 something. So it's about 22, let's say. Now that we've identified those frequencies on the two different plots, we can use those to actually read off basically the opposite word for the stability. Meaning, if we look at the gain curve and we read down, that will actually give us our phase margin based on the gain crossover frequency. That will give us our phase margin. Meaning, we now drop down to a value of 2. Let's just do it right here at 2. And now we are looking at that phase difference between the phase curve and minus 180. How much phase can we move through in order, or before we reach this combination of 1 at minus 180? And that will give us our phase margin. What do you see that being? Again, this is back of the envelope. And hopefully you can see it a little bit. We have 45 degrees right there. So each grid piece is 45. And if we just did it very quick eyeball, that looks like it's about a third of the way in between, or 2/3 of 45. And if we divide 45 by 3, that's 15. So if we take 2 of those, we really have 45 plus 30. Is that making sense? Or our phase margin is about 75 degrees. Are we comfortable with that? And it's a positive value, and that's a good thing. And what we will learn is that if we compared this to a zeta value, you're very comfortable with zeta and percent overshoot on a second order system. Here, if you multiplied that phase margin by 0.01, that gives you something like your zeta value. So this would be like a zeta of 0.7, which corresponds to what kind of an overshoot behavior for a second order pure two-pole system. That's a 5% overshoot. So this would have a pretty good response. It's a fairly stable system based on the phase margin. What's our gain margin curve, or what's our gain margin value? Now we go over to where we crossed the phase through minus 180. We go up to that frequency, which let's say is about right here. And we say, how much gain can we increase before we reach 0 dB, or a magnitude of 1? In this case, the grids or the marks are about 50, and that looks like it's a little bit more than half of that grid. So we're more than 25 dB of gain margin. Maybe we're not 60% of the way, but we're close to that, aren't we? So it's like 25 to 30 dB of gain for our gain margin. Questions on that? How we found that? Did anybody get close to that? Or did you? Well, now do you know how to find gain margin and phase margin? This might be an easy 10 points on the final. You identify your two frequencies, and then you find how much we can adjust the phase and the gain in order to satisfy this 1 at minus 180, and that gets us right to the point of stability. And that's our margin. Meaning we like to have that gain margin below 0 dB. We need a fair amount of gain margin, and that's just like the knob. If you were thinking of a root locus plot, How much can you crank up the gain before your poles migrate into the right half plane? That's the same idea. Now, if we had this system, now I have to figure out where it is. Got lucky. Can we determine anything more from that system? Can we identify G of S given this Bode plot? Or can you tell me anything about G of S by looking at the Bode plots? And now you may just be looking for a few different characteristics or system properties based on what you can see in the phase curve or the magnitude curve. For example, the phase curve being at low frequencies at minus 90, what is that telling you? Or is it telling you anything? Or what will it be telling you after this lecture? Now I'm saying this is giving us a clue as to what's one part of our G of S. Another part is at high frequencies, what's the phase look like? Where is it going? And what does that tell us? As we go to high frequencies, what are we really sort of saying is happening in our transfer function? All of our, let's say, poles and zeros have now kicked in, and now they're all contributing their phase, and we end up at minus 270. What does that tell us about our overall system in terms of poles and zeros? We have at least a pole zero excess of 2. What does each pole contribute in terms of phase? Minus 90. So now we have at least, well, we do have a pole zero excess of 3 because we are ending up at minus 270. All those poles, we have, let's say, 3 more poles than zeros. Each of those poles give us 90 degrees, minus 90 degrees. So we have a pole zero excess of 3 in our overall transfer function, just based on seeing that curve at minus 270. The fact that G of J omega is approaching minus 270 degrees for large frequencies is implying a pole zero excess equal to 3. What about this phase of G of J omega being minus 90 degrees for small omega? Now we have a pole at the origin, don't we? We're assuming that that minus 90 just keeps that same behavior for lower and lower frequencies. This now says that we actually have a pole in our G of S at the origin. So if we were doing this, we sort of are saying, oh, G of S looks like an S, and then it looks like that, and probably some gain. And if we had another zero factor, we would have to have another pole factor, because eventually we need to end up with our poles minus our zeros being 3. Is that making sense? We have a pole zero excess of 3. And that minus 90-degree phase for small omega says, oh, you've got a pole at the origin. It's by itself. Can we figure out any of this other unknown parenthetical behavior by looking at this? Remember what happens with poles in contrast to zeros. Poles go down in magnitude. They also make the phase go from, let's say, 0 to minus 90 for each linear factor. Zeros have a tendency to kick things up or to go up. Is anything in that magnitude and phase, either of those plots, wanting to go up in a slope? Is the slope ever, does it look like it's wanting to sort of go up? No. So that would sort of say you may not even have any zeros in this system. You may just have poles. If that's the case, then in this identification of G of S that we are trying to perform, we can basically say, oh, let's not worry about a zero, so now maybe we just have 3 pole factors. We've already identified one of those. Yes? No, we can't say, the question was, can we say this is a pure system? We can't yet, but we're trying to determine what we can unravel from the frequency response. And what we are doing is we're saying if there are any zeros in this, they're pretty well hidden. I don't see the magnitude or the phase tending up anywhere in slope. And that's sort of what that is what a zero does. So if that's the case, now we say, well, because of minus 90 degrees, we know we only have one pole at the origin. We could now sort of say, well, let's look at this. And if I just kept going at that slope, that would just be what would happen with one pole. Which means, where do I start sort of varying? And that was, here's where you would want your ruler. And I don't have a ruler. But where does that slope start to now deviate? Do you see where it's starting to sort of break in the magnitude? It's starting to, the slope is changing at different places. It looked very gradual until I started to draw these straight line extensions. And now my green curve is saying, oh, if I just had one pole at the origin, that's what I would see. But, oh, I'm seeing something else, and we know we're going to end up with 3 poles total if we don't have any zeros. Then where does the green and the black curves tend to sort of start breaking? We just did a rough, and I could be 3 dB down right at the break, because that's what a pole does at the break. It's actually 3 dB down from our straight line approximation. So in this case, it looks like 10 is a pretty good guess for where I first break beyond that pole at the origin, which it never breaks, does it? A pole at the origin just keeps sloping and sloping. So this is basically saying that I might have something like an SO, and what color was that? That was black, wasn't it? I better be consistent. S over 10 plus 1. That would give me a linear factor with a pole at 10. And where does this other red curve start to come into play? And that one, it may not, I've probably muddied up the waters, but it looks like 80. I know what it should be, and it's a little less than 80. So I know that I've not drawn this very well with my rough sketches, but if we just had to do it, you would say, oh, it's about 80, right? So now you would say, oh, this is now, whoops, that was red, wasn't it? I'm just trying to stay awake here. I'm trying to make it interactive. What else are we missing in G of S? K. How do we find K? Well, K is all over that magnitude plot, but we could start to say something like, where does it go through 0 dB? Because then we know the magnitude of the transfer function at that frequency is 1. We now can say, oh, if this is our curve, if we looked at G of J omega, where the magnitude is equal to 0 dB, let's say this is now the omega c, the 0 dB crossing. If we plug that in up here, or if we look, where am I crossing 0 dB? What frequency, roughly? Looks like about 2, doesn't it? So now we say, oh, omega c is 2 radians per second. That's what we actually used for the gain crossover, wasn't it? So let's stick with that. So now we know that in this model that we've identified, we now need to make the gain K be such that all of these combinations, when J or when omega is 2, we need to end up with a K that gives us a magnitude of 1 for all of this, because we know it's 0 dB when we take 20 log of that magnitude. If we now go with that, we say we have a G of J omega, but we're going to evaluate that at omega equal to 2. This is now K. We didn't have any 0 factors, but we had a J omega, so we're going to say there's J2. Then we had a J2 over 10 plus 1 and a J2 over 80 plus 1. And what have we agreed to do? We've agreed to basically neglect these other linear factors as long as the imaginary part is less than 1, when it's not equal to the real part, which is 1. So J2 over 10, that's basically 0, is what we're saying. It's 0.2. So we're just going to say that factor becomes 1. J2 over 80, that's even closer to 1. We're saying that these we are just going to approximate as 1. And now we want this entire thing to equal 1. Yes. The whole parenthesis is 1. Yes, that's a good question. My notation is not very clear. One looks like that and the other one doesn't. But now I'm saying that this piece right here, we're saying that's approximately 0. This piece is even closer to 0 because 2 is so much less than 10 or 80. That's the approximation we're making. And if that's the case, now we can quickly identify what K is. And I didn't do this quite right. I need to make sure that I'm looking at the magnitude of all of this. And now if I have the magnitude of J2 downstairs, I can get rid of that J because it just has a magnitude of 1. And this now says that K is equal to 2. And now I've identified my system. I now can say that G of S via system identification is 2 over S, S over 10 plus 1, S over 80 plus 1. Now I'm curious what my system actually was. So did I approximate the s over 10 plus 1 and the s over 80 plus 1 as 1 to be simple? Yes. But you could incorporate that if you wanted to, but here for the back of the envelope, I'm just going to say I'm going to neglect those because they really haven't kicked in at that low frequency anyway, have they? So they're not really impacting the magnitude at that frequency where the crossover is because they haven't kicked in until 10 and 80 anyway, so I'm going to just neglect their influence. Is that making any kind of sense? Now if somebody gives you a Bode plot, are you going to be able to identify the G of S from that? And what did we do? We simply played with or tried to. And what you can do is you can start to check your work by correlating the phase curve with the magnitude curve. If you've now speculated that you have a pole at 10, when is the phase curve going to start changing? Slope. If you have a pole at omega equal 10, when is the phase curve going to start changing in slope? What do we know about the phase curve and how it transitions? Pardon? It starts to give you phase contribution in our straight line approximation, and that's what it is. It's a straight line approximation. It actually kicks in before that a little bit. But in a straight line approximation, we basically say the phase starts influencing the phase curve a decade before the pole, or zero, and all the way through a decade after. That's where it impacts the slope of our phase. So if we had a pole at 10, omega equal 10, we would start to see the phase changing a decade before 10, which is 1, and that pole would quit introducing its phase slope at a decade beyond 10 or at 100. And now if these things are all close or they're within a decade of each other, they're going to start playing, they're going to start singing together, aren't they? They're going to play together, and it's going to mess things up relative to, oh, I can't see exactly where this starts and stops. Well, that's because they're transitioning, turning off and on in overlapping regions of the frequency axis. But here, it does look like, and really this straight line approximation is in error by about 6 degrees in terms of our actual phase. It's giving us about 6 degrees of phase before we in the straight line approximation even acknowledge it. Meaning there's 1, and that does look sort of like where the phase starts to change. So you can start to check, and this is true, these relationships for minimum phase systems as far as the phase curve is going in the negative direction like we thought. If we actually went in and wanted to see what this system might look like, I actually built this system as a numerator of, well, I actually didn't build it in time constant form last night. I built it in pole zero form, but I'll try to put it into time constant form now. We said we had a gain of 2, didn't we, in the numerator? And our denominator was a combination, well, it was 3 different factors, and I don't want to multiply those out, so I'll let MATLAB multiply them out via the convolution function. That's how it multiplies polynomials together to keep track of all the coefficients. I had, what did I have? I had a pole at the origin, didn't I? So let me do that. Do I want to nest my convolutions? Oh boy. There's a pole at the origin. And what else did I have? I guessed a pole at 10, didn't I? So that's now 1 divided by 10 and 1. And now what I want to do is actually convolve that with a third factor. So I hope that I have, oh, how, sorry. So this is now my first convolution, if I can keep track of my parentheses. And now the next one, where did you guess it was? 80? So 1 over 80, 1. And now I should have my numerator and denominator factors. I can say my transfer function now is made up of N1 and D1. And I could actually now say Bode G1. And then you could go get coffee or something and wait for MATLAB. Oh, there it is. Whoops. I want to see a grid on that. But now this is what MATLAB has produced. And that doesn't look too bad. I mean, we're not doing this very closely or comparing it with the earlier one. I think my poll in the one last night was at 50, not 80. But the others were right on. And look at where we're crossing 0 dB at 2, etc. with our identified system. You can even tell MATLAB, you can say, you know what, I know my MATLAB, whoops, we don't have a figure. We need a figure, a new one, so I'll do the second one. You can actually cheat and just say, would you give me the margins? And if you do a margin command, it will tell you your gain margin and your phase margin immediately. And here we have a gain margin of 33, so that poll at 80 has kind of messed us up in terms of our gain margin maybe. And what's our phase margin? Pretty close to what we guessed, right? We guessed 75, it's 77. And where did those occur? Well, the phase margin occurred a little shy of 2, and we guessed 2. And the gain, or the phase crossover frequency was 28, and we had 22, but that's a function of us over guessing or estimating that pole at 80. But we've done a pretty good job. You could now control your system with this, G of S, just from that frequency response data. What else could you do? Well, you could say, you know what, I'm really comfortable with the root locus, and there's my root locus for the system that you identified. And does that look consistent with the Bode plot? How come we have branches in the right half plane? I thought the system was stable. Pardon? For a gain of 2. So the root locus is telling us what the closed loop poles will do for all gains, right? From 0 up to infinity. And we just had it for a fixed value of 2 in our Bode plot. It has to be a fixed value, and then you sketch. You then, with these 3 x's, you now walk up the imaginary axis and you find the magnitude and phase at each of those points on the imaginary axis, and that gives you your Bode plot. Okay? And we could even say something like, well, I'm tired of that domain, and go into the time domain. And you could say, let me see, whoops, If I say step of G1, what's going to happen? I'm going to hit the system in the open loop. And that's not what I'm assuming is happening. I'm assuming I have a closed loop system. I have to now create the closed loop transfer function from this open loop transfer function that I've identified in order to generate the step response. So let me back out of that and say, let me get my closed loop transfer function. T1 is now the feedback combination of G1 with unity output, and feedback is assuming negative feedback, so you don't have to say anything other than if your feedback path is just a unity, it's just 1. If it was an H, that would be your H right there. But there's our closed loop system. We could even say, where are the poles of our closed loop system? And they're now at minus 80.2, which is correct with our root locus. And the other two are between the origin and minus 10, which is what we knew they should be. And we haven't yet cranked up the gain to get off the real axis in our root locus sketch. So the real axis is, from this curve, from the root locus, we don't know what the gain is unless we actually evaluated the gain at a particular point. But if we now we know that for this particular transfer function and those poles and zeros, our gain is 2, and with a gain of 2, we've moved from the origin to minus 3, roughly, and from minus 10 to minus 6.8. So those two are coming together, and they're still on the real axis. If we cranked up the gain, if that K became 5, then we might start to go imaginary, or have imaginary parts to those two. Because the root locus tells us if you crank up the gain enough, you're going to start going unstable. And one of the poles, the third pole, is just migrated very gingerly beyond minus 80 for that gain of 2. It's at minus 80.28. And that's what the red branch of the root locus is indicating. Now I said we would sketch the step response, and I don't want to, did I already do a figure window? I did, so I have a blank figure, but it'll overwrite figure 3, so let me go back to my blank figure and now issue the step response. And there is our behavior, and it's not a pure 2-pole system, it's a 3-pole system, isn't it? And our overshoot is less than 5%, isn't it? This is like an overdamped, it is an overdamped system. But it's somewhat consistent, and you could start to find your different characteristics if you wanted to. If you right mouse click, you could say, what's the settling time? And it identifies where it goes, and then you click on that and you say, oh, my settling time is 1.54. And you go, oh, that's just right, or that's not enough. And then you have to figure out what to do next. Questions on this system and how we are able to identify a system from the Bode plot. What if we try it again? Can you now identify this system? This is just the magnitude. We're not even going to look at the phase curve. We're just going to look at the magnitude curve. And can you tell me anything about the system transfer function based on this magnitude plot? We do have a positive slope, don't we? So that means this system is a little different than the previous system. Do we have, at low frequencies, what's our slope doing? of the magnitude at low frequencies. At very low frequencies, let's just assume that it continues in the direction that it started. Is our magnitude sloping at low frequencies? No, it's constant at minus 40 dB, isn't it? Does that mean anything? Does that tell us we have a polar zero at the origin? What's a pole at the origin give us at low frequencies? I want to start doing gestures. It's always sloping, isn't it, at 20 dB? We don't see anything sloping from a really high mountain at low frequencies. So we don't expect a pole at the origin. Is anything coming up from the depths of the ocean at low frequencies? That's what it would do if it was a zero at the origin. It would always have a plus 20 dB per decade. And it's not, it's flat. So this says we don't have anything happening at the origin in terms of poles and zeros. And we can identify the system gain based on that particular magnitude at that frequency. Now, how are we going to determine? You said we have a positive slope. Do we have any negative slopes? And actually, once we start sloping, do we change slope? That's really what we're after. We're saying, do we have any changes in slope? So we're going up, and we don't just keep going up, do we? Which is what a zero factor would do. We start to flatten out. So we've had a pole introduced after the zero, and then we actually start sloping more. And if I ask you what's the pole zero excess, how would you determine that based on the magnitude plot? How do you know there's two poles? Did everyone hear that on the audio? I'm doing hand gestures. That's not going to translate very easily over the video recording, is it? So we have a constant, then we go up, then we go flat, then we go down. What's the pole zero excess? That's not the same question as the number of poles. We've sort of said it leveled and went down, so that did give us our two-pole estimate, didn't it? And it went up at one point, so we have a zero. And now we want to verify, do we have a pole zero excess of 1? Because we have two poles and one zero. How could we verify that we have a pole zero excess of 1 from the magnitude plot? So we look at high frequencies and we try to measure that slope at high frequencies. And what would you want that slope to be? You would want that to be going down at 20 dB per decade if you had a pole zero excess of 1, because you have one more pole at high frequencies relative to the zeros. And that one pole is contributing 20 dB per decade. You would use this piece right here to figure out what the gain is. This says we have a zero. This says we have a pole. This says we have another pole. And now you could extend those straight lines and start to identify where these breaks are occurring. Where is the zero occurring? Roughly. And my straight line is terrible in terms of matching with so the zero, and here what you would do is you would say, oh, let me extend that, and then where am I sort of 3 dB away from where it breaks? And in this case, it is at 0.1, isn't it? It's 10 to the minus 1. Our zero is at 0.1. And then we would say, where is our pole going to be? And now we see there's like this 3 dB difference between where it's flat and where it's at about 1, isn't it? So now we have a pole at 1. And then when does our second pole kick in? At about 10. Boy, I was using round numbers when I sketched this curve, didn't I? Do you see that? And then how would you get your gain? You would get that from minus 40 dB. You would say all of these pieces give me, at this frequency, a gain of minus 40. And you have to get that into absolute numbers instead of in dB. And you can do that by raising things 10 to the power. Okay, so now you're experts at system identification in the frequency domain. After lab 1, you knew system ID from the time domain. Now you're really experts on system identification. Question? Pardon? How can I tell if there's a pole at the origin? Anyone want to help? There's several ways. One is it sloping at low frequencies, and is that slope coming down at 20 dB per decade? The other, which I didn't give you, is the phase curve. If you look at the phase curve and you're at minus 90 degrees in phase at low frequencies, you go, I've got a pole at the origin, because that pole contributes 90 degrees and it's downstairs, it's minus 90. Enjoy your break. Thank you for showing up. Nothing really magic happened, even if you were all in the right half plane. Thank you.